Have you ever wondered why two seemingly identical batches of powder can behave completely differently the second they hit the fast-paced factory floor? I mean, you test them in the lab, they look identical, they feel exactly the same, but the moment you actually put them into production, boom, one flows perfectly and the other literally jams the entire line. So, why does this happen?
Welcome to this explainer. Today, we're going to bust the myth that powders are just simple solids. We're diving deep into exactly why powder properties absolutely require advanced testing, and as you'll see, how getting this wrong can cost manufacturing facilities millions in ruined product and crazy amounts of downtime.
We've got a great roadmap lined up for us today. We'll start off by looking at the incredibly complex nature of powders, move on to why traditional testing completely fails us, look at some real-world manufacturing disasters, and then finally wrap up with the dynamic testing solution.
All right, let's jump right into our first section and talk about the complex nature of powders. Because honestly, it's rarely what people initially assume.
See, a powder is not just a single solid entity. It's essentially got an identity crisis in a jar. It's actually a highly complex mixture of three distinct phases. You've got your solids, which are the particles themselves, you have liquids, which is usually surface moisture, and you have gases, basically the entrapped air sitting right there between the particles. The way these three phases interact determines exactly how the bulk powder will behave. Depending on the situation, they can deform like a solid, flow like a liquid when aerated, or, believe it or not, even be compressed like a gas.
Now, there are three major mechanisms that restrict particle independence and resist flow. First up, mechanical interlocking. This is where irregularly shaped particles physically hook together, almost like pieces of a giant puzzle. Second, we have interparticulate cohesion. These are the actual forces bonding those contacting particles together. And third, liquid bridging, where moisture actually creates tiny capillary bonds between the particles. Every single one of these restricts movement and causes major flowability headaches on the floor.
This brings us to an absolutely crucial point. Powders actually retain a stress history. As the saying goes, powders have memory. Their current flowability is heavily dictated by their past. For example, if a powder was recently vibrated and tightly consolidated in a keg during shipping, those particles are packed tight, the air is squeezed out, and it's going to be highly resistant to flow. On the flip side, if it was just aerated, it might flow beautifully. The physical and chemical properties of those particles haven't changed one bit, but the behavior is radically different, based purely on its stress history.
So, moving on to our second section, let's look at how this crazy physical complexity completely breaks traditional testing methods.
The core problem here really comes down to a fundamental mismatch in environments. In the lab, static tests evaluate powders resting gently under gravity at just a single moment in time. But dynamic production environments, they are completely different animals. The powder is confined under immense pressure in a hopper. It's subjected to high, varying speeds on a filling line, and it undergoes nonstop cyclic mechanical stress. A test optimized for resting under gravity simply cannot and will not predict behavior in a violent, high-speed factory setting.
Traditional metrics, things like the Angle of Repose, Carr's index, or the Hausner Ratio, are still widely used today, mostly because, well, they're quick and easy, but they have severe structural limitations. The Angle of Repose measures a powder pile dropping freely onto a surface. That totally ignores the massive confinement pressure inside a silo. Carr's index and the Hausner ratio measure compressibility entirely at rest, missing entirely how the powder reacts to the changing speeds of a feeder. Long story short, they structurally fail to predict how powders act under dynamic manufacturing stresses.
Because they're entirely static, these tests miss a massive amount of critical information. Think about it. If your powder fills perfectly at 60 units per minute, a static test won't warn you that flow resistance might drastically change and cause fill weight drift at 120 units per minute. They also miss whether a powder breaks down during long, repetitive runs, or if a hopper discharge failure is caused by cohesion versus structural arching. Those are two very different problems requiring completely different engineering fixes. And they certainly can't tell you if the powder is going to densify and form a solid cake if you just leave it in a silo over the weekend.
Now let's explore Section 3, where we'll look at the costly and frankly chaotic real-world manufacturing disasters caused by relying on those inadequate tests. Imagine a seasoning powder in a busy food processing plant. On Friday, the relative humidity is sitting at a nice 20%. The powder is dry, free-flowing, and processing perfectly. But over the weekend, the humidity climbs. By Saturday at 50% humidity, capillary bridges start forming between the particles. By Sunday, at 80% humidity in a tropical climate, those bridges merge into the funicular regime, literally turning the powder into a cohesive, caked mass. By Monday morning, your hopper is completely jammed. Instead of processing food, you're paying a massive cleaning bill to chip out a solid block of seasoning. No way anyone wants to deal with that on a Monday.
And the stakes are even higher in the pharmaceutical industry. When powders flow poorly through a hopper here, they don't just jam up the works, they can actually segregate. This means the vital active drug particles physically separate from the filler excipients. The terrifying result of this? Poor content uniformity. You end up with some tablets having absolutely zero active drug, while others become dangerously toxic, overdosed batches.
This cascading failure applies to cutting-edge modern tech like 3D printing too. Intricate metal parts created through additive manufacturing rely on spreading incredibly thin, sequential layers of metal powder over a build plate. If that powder doesn't flow perfectly homogeneously, it causes discontinuities, layer porosity, and catastrophic structural weakness in the final precision parts. Funnel-based tests are just way too operator-dependent to predict this with any real accuracy.
All right, it's time for our final section, where we're going to reveal the ultimate solution for accurately predicting how your materials will actually perform.
Dynamic testing is an absolute game changer. Why? Because it directly maps those high-stakes production questions to the exact multivariable dynamic measurements you need to solve them. By mimicking the actual factory environment, dynamic testing gives you real, actionable answers. Are you worried about fill weights drifting at high speeds? Just measure the speed sensitivity ratio. Need to know why a hopper won't empty? Measure the cohesion index and bridging factor separately. Terrified your product will turn into a brick over a humid weekend? Use a consolidation and caking rig to test its strength under load over time.
This brings us to vital lab equipment like the automatic ring shear tester. This instrument moves completely beyond those old gravity tests. Instead, it precisely quantifies a powder's shear strength and internal wall friction, which is basically how the powder shears against the actual material of your process equipment, under controlled, realistic normal stresses. This allows engineers to safely design hoppers and silos that, actually work.
So, the true power of dynamic powder rheology lies in measuring the powder's resistance while it is actively in motion, usually by rotating a precision blade right through the sample. But crucially, it uses a conditioning cycle first. This gently moves the powder to erase that problematic memory we talked about earlier, giving you a clean baseline. From there, you can measure exactly how the powder reacts to aeration, varying compaction states, and speeds, which gives you a true multi-parameter profile.
Ultimately, these multi-parameter tools allow scientists and engineers to detect tiny, almost invisible batch-to-batch variations that single-point static tests miss entirely. It takes the guesswork out of process engineering. Instead of just crossing your fingers and hoping a new batch will run, or dumping expensive anti-caking flow aids into every recipe just to be safe, manufacturers can pinpoint exactly what is needed. This optimizes formulations, minimizes waste, and saves immense amounts of money in equipment downtime.
I'll leave you with this final, somewhat provocative thought to take away. If you are only measuring your powders while they sit completely still on a lab bench, do you really have any idea what they'll do when the factory machines actually turn on? Thank you for watching this explainer. Rethink your testing, and we'll see you next time.